Hello and welcome to another lecture from my class, PSYC 440-640, the class that's called Experimental Methods, but is really a class on univariate data analytic techniques from a model comparisons perspective. As usual, I'm beginning with a comic from phdcomics.com, which, it has to do with thinking, therefore it has to do with psychology, therefore it kind of seemed appropriate as a way of starting this lecture. And as someone who tends to overthink most things in my life, I can appreciate some humor here. By the way, if you're enrolled in my class, or I guess if you're just going to follow along with some of the examples that I use, go ahead and start SPSS on your computer now, or whatever your preferred stats program is right about now. Okay, this class is called Introduction to Interactive Models, and really what I'm going to try to do is continue the discussion of multiple regression while introducing a really important idea, and that is interactions between predictor variables. Before I get there though, I want to do a quick review of what we've covered in the last and kind of previous lectures. I've been talking about multiple regression, which is just regression analysis when there's more than one predictor variable, and if you need me to make the case for it, I would argue that multiple regression is very useful because most outcome variables that we study in psychology and the behavioral sciences are multiply determined. That is, there's more than one predictor of most of the stuff we care about, so it's nice to be able to make statistical models that represent that multi-determined nature. Multiple regression allows us an opportunity to exert statistical control over potential confounding variables by bringing them into the model and then examining whether our main predictor variable of interest makes a significant contribution to predicting the outcome while holding another variable constant. And depending on how you do your multiple regression, especially if you do hierarchical multiple regression, you can evaluate predictor variables in a particular order, which can be useful for answering certain research questions or testing certain research hypotheses. Last time I talked about different approaches for multiple regression, and if we want to kind of think about them in sort of different ways, one way would be to say, well, there's kind of regular, or it's sometimes called simultaneous multiple regression, where the predictor variables are entered all at the same time. And in a sense, this is researcher driven in that you decide as the researcher, as the data analyst, to bang all your predictor variables into the augmented model in one step, or in what SPSS calls one block. Again, this is sometimes called simultaneous multiple regression in some textbooks or websites that I've seen. We can contrast that to hierarchical, or what's sometimes called sequential multiple regression, where predictor variables are entered or even sometimes removed in a specific order. There are different flavors of hierarchical or sequential multiple regression. The ones that I favor and the ones I emphasized in my last class are essentially the researcher-driven approach, which is just a researcher-driven hierarchical multiple regression where you, based on theory, or I guess based on previous research, enter particular predictor variables in an order that is useful to you for answering questions or testing hypotheses. There are in SPSS and in other stats programs computer-driven or kind of algorithmic options where SPSS, or the software that you're using, will add and remove predictor variables until it, the computer arrives at kind of a sweet spot, at kind of a model which by its criterion optimally describes the outcome variable. These aren't terrible to do, but again, I encourage people to make statistical models based on theory and based on research, making decisions about whether or not to include predictor variables rather than just starting with a very large number of predictor variables and saying, okay, SPSS, you sort it out. You can do that, but then you often end up in a situation where SPSS gives you a model and you as the researcher kind of have to justify why some variables are in the model and some aren't, and you create kind of a post-fact story as to why this all worked out the way it did. And I think those are not very those often lead to not very interesting interpretations. Okay, so assuming that you kind of get the basic idea that we often in multiple regression choose an order, or maybe have SPSS choose an order for us to enter these variables, enter these predictor variables, you might be wondering, well, how do you choose what order to enter variables in. How do you decide which variables go in step 1 or block 1 and which variables go in step 2 or block 2? Well, there's no really precise answer to this question. It really depends, like so many things in statistics, on your research design, on kind of the rationale for your study. Sometimes, if you have predictor variables that have a natural kind of temporal order with each other, you might choose to put earlier predictor variables into earlier steps and then later predictor variables into later steps of a model. That's possible to do, assuming those variables aren't dependent with one another. You might choose to enter the old ones in the first step and the newer ones in the second step, or so on. What is also sometimes done is you enter predictor variables in terms of a logical order. If you have predictor variables that have a certain sort of presumed connection to one another in a chain of causal connection, then you might choose to enter the earlier elements of that chain in the first step of the hierarchical sequence, and the later steps or links in the chain in the later steps of that hierarchical process. So that sometimes happens, this kind of ordering via temporal order or logical order. At this moment, I'm kind of struggling to think of good examples of that. Probably after a few slides it'll come to me, and then I'll have to decide whether to stop and go back and edit this slide. We also can make decisions, and this is something I have mentioned before, and this is something I have seen a lot before, based on research questions or based on hypotheses. Sometimes it is the case that when we are a researcher, when we're a data analyst, we have particular predictor variables that are for us of primary importance and others that are of secondary importance. So you might have some main predictor variables that you're principally interested in, and then some other predictor variables which you gathered but you consider kind of secondary or supplementary. You're kind of interested in them but not so much. If that's the case, then you might enter your main predictor variables in an early step, maybe in a block together in block 1, and then maybe your secondary variables in block 2, figuring that you're really going to focus mostly on that first augmented model. And if something kind of interesting comes up in that second augmented model when those other predictor variables are added in, you might report that model or describe that model in your results section and hopefully characterize it as a kind of an exploratory analysis, since you weren't really that interested in it. Another thing that happens sometimes in data analysis in psychology, other sciences I'm sure, is we ask the question, does a particular predictor variable predict the outcome variable above and beyond other predictor variables? So we might say, to what extent does the drinking to cope motivation predict alcohol problems above and beyond gender, or vice versa? I forget exactly how the example worked in the last lecture. In those cases, what we would do is enter the first predictor variable in the first block, and then enter the other predictor variable, the one that we're kind of interested in the second block, and see, does the model improve in terms of its fit when our other predictor variable is added in? Does adding in this other predictor variable incrementally improve the fit of the model? That's often the way those type of analyses are framed. So the point I hope you're getting from this slide and from the previous slide is that if you're using the researcher-driven approach to entering predictor variables into a hierarchical regression, it's kind of up to you to choose that order, and you can choose that order based on different reasons. It's up to you, again, to choose and hopefully to explain to your colleagues, to your readers, if they're reading a paper that you've written, why you chose the order that you chose, and hopefully that makes sense. Bearing in mind that there are often other approaches to entering those variables which could be justified with other rationales or other kind of explanations. Again, this often happens in statistics. There's no precisely right way to do an analysis. There are different ways, and they have different benefits or costs, trade-offs, if you will. Anyway, with that rather rambling review out of the way, let's go on and give a quick overview of what I'm going to cover today. I want to talk a little bit about multicollinearity, which is a big word for a topic that we've actually already addressed, and one that's important when we consider multiple regression, or really any sort of analyses where we have more than one predictor variable. Then I'm going to go on and start talking about interactive models. These are models in which predictor variables can interact with each other, and they're very important and very interesting, and I'll actually be addressing them more and continuing to address them in subsequent lectures. So first off, multicollinearity. Again, a big word, but it's a word that refers to a concept that I've talked about before. And that concept is the relationship between predictor variables. Now, in the last lecture I said it's sometimes the case, maybe especially in experimental designs, that we can have predictor variables which are perfectly uncorrelated with each other, which share no overlap or relationship with each other, which are orthogonal with respect to each other. That's less common in non-experimental research, because many of the predictor variables we study, which we sort of measure as they come in the world around us, tend to be at least a little bit correlated with each other. If these predictor variables exist in perfect multicollinearity, that is, if they are perfectly correlated with each other, then essentially they're interchangeable. If you had two variables, self-esteem and self-likingness, which are two variables which are so, although they're named differently, are so similar in terms of what they are at a kind of a deep level and maybe how you measure them at a more surface level, that they are perfectly correlated, then essentially they're the same thing. You may call them different things, but they're the same thing. Now, happily, this rarely happens in real life, that we have variables which are perfectly correlated with one another. But what does happen in real life is, at least in non-experimental designs, often is that we have less than perfect multicollinearity. Situations in which our predictor variables are modestly correlated with each other. Now, this isn't necessarily bad, but it can lead to problems where the regression coefficients, those little b's, become a little bit untrustworthy, meaning it becomes a little bit difficult to interpret what they mean if you have a model which consists of multiple predictor variables which are to some extent correlated with one another. Those variables are to some extent overlapping, and like I just said, it becomes a little bit difficult to talk about their relative importance towards the prediction of the outcome variable, because they're sharing in a sense with each other. So if you're doing a set of analyses, you may be wondering to yourself, how much multicollinearity do I have? Well, one thing to do, and probably one thing you should do anyway, just as a matter of simple exploring the data, kind of descriptive statistics, is look at the correlations between your variables, especially between your predictor variables. And if you have predictor variables that are highly correlated, if they're simple Pearson correlations, or in the 0.7, 0.8, 0.9 range, then you have variables which are really, really highly correlated, and that's going to almost certainly lead to problems with multicollinearity. Either the regression that you're trying to run in SPSS won't resolve properly, you may even get an error result from the analyses, or even if the model seems to resolve, you get regression coefficients, you get significance tests and so on, you might still really struggle to describe the relative contributions of these two variables, or two or more variables that you have, given their high degree of overlap. So again, one thing you can do, and really one thing you should do, is just look at the correlations between your variables. You should probably be doing that anyway. There also are a number of calculations the SPSS and other stats programs I'm sure will give you, which we sometimes call collinearity diagnostics. They are maybe more generally lumped in with the other regression diagnostics, and they include things like variance inflation factor. Variance inflation factor is just a calculation which tries to express how multicollinear groups of variables are, groups of predictor variables, and by convention we should be concerned if the average variance inflation factor, we get a score for each predictor variable we have, and if the average of all those VIFs is greater than 1. And we should also worry if the VIF for any given variable is greater than 10, like if it's just really big. That's suggesting a problem with multicollinearity. There's another calculation which is called tolerance, which is just 1 over VIF, and here we want to look for variables with tolerance of less than 0.2 or really even less than 0.1. Those are calculations for tolerance which suggest to us problems with multicollinearity. The way I like to remember this is, tolerance is like the model saying, I just can't tolerate this variable because of all this multicollinearity. If the model has low tolerance for this variable, then that's a problem. Or at least that's potentially a problem. Let's consider an example and look at how this might work. Imagine you're a developmental psychologist studying emotions, and you're doing a non-experimental design in which you have two predictor variables. You've got self-esteem and positive self-image. And as you can well imagine, these are variables which are probably pretty correlated with one another. And you've got an outcome variable, which is happiness. And so you might be wondering, to what extent do these predictor variables predict the outcome, happiness? Like I said, you might guess that these variables are highly correlated, and indeed in the data set that I made up, this is fake data, they are very highly correlated. They're correlated at the level of almost 0.9, and that's quite a lot. Now, it's possible that each of these things are measuring something slightly different. Maybe there is some kind of philosophical difference between self-esteem and positive self-image, but given their high correlation, it's also clear that they're measuring a lot that is the same. There's a lot of overlap if you kind of picture this like a Venn diagram. Now, if you're enrolled in my class, you can find on Blackboard a data set called Multicollinearity, which I'm using for this example. It's just data that I made up to illustrate the point. If you're not enrolled in my class, and if you want to, you can just pause the video right now and copy these values into SPSS or into whatever stats program you're using, and you can play along with the analyses that I'm about to show. The basic idea here is we're trying to predict happiness from these two predictor variables which we know or which we have found are highly correlated with one another. What we would probably do is just enter them simultaneously into a multiple regression, not fiddling around with order or anything like that. However, just to briefly illustrate my point, what I'm going to show on the next slide are actually three separate analyses. One in which one predictor variable, self-esteem, was entered, the other in which the next one, positive self-image, was entered, and a third in which both of them were entered. So two simple regressions and one multiple regression. And I'm just doing that to kind of illustrate a point. And the point is that positive self-image is a significant predictor of our outcome variable happiness, but not when self-esteem is entered into the model. So you can see there at the bottom, if we're looking at our multiple regression, that includes both of our predictor variables. Positive self-image, which formerly had a significant value for its slope, now does not. You can see that the significance level is much higher than the usual criterion of 0.05. Now, why is this happening? Well, if you didn't already know, you could ask SPSS to give you part and partial and zero order correlations, and that would look like this, basically running the analyses again and just asking for that additional information. And what you can see here is that both self-esteem and self-image are correlated with happiness. That's good. We want predictor variables that are correlated with outcome variables. If not, then why are they predictor variables? But what's not so good is that positive self-image has basically no relationship with happiness after self-esteem has been partialed out of happiness. So if we take the amount that self-esteem and happiness overlap, and we remove that, then there's very little left over that positive self-image can be related to. The part or semi-partial correlation between positive self-image and happiness controlling for the effect of self-esteem on happiness is really, really small. So it's basically a pretty small correlation. We also, here I'm just running the analyses again, and this time asking for some collinearity statistics, which you can get in SPSS. Obviously you could do these all in one go. I'm deliberately not, just to save space on the screen. I'm asking for those collinearity diagnostics, and you can see here that the tolerance for each of these variables, and they're going to have the same tolerance because there's only two variables, so each has the same tolerance for the other, is around 0.2. And so that's fairly low. That should concern us. And we can see that variance inflation factor, VIF, is quite a lot higher than 1, and that of course should also concern us. Now, I said before that you would probably do this analysis as a simultaneous multiple regression, but if for some reason you did a hierarchical multiple regression, that is, entering one predictor variable in one step and then the next in the next step, you would see in the output a table called excluded variables. And if you look at this table, you can see that what SPSS is doing is it's suggesting that you exclude positive self-image because of its high VIF and its low tolerance with the other predictor variable, self-esteem, which is already in the model. So it's kind of giving you this hint here like, hey, these variables have high multicollinearity. We want to, or we should probably want to get rid of one of them. Now, the important point here is that you should think about your predictor variables. I mean, you should be thinking about this from the very earliest stages of research design, not just when you finally get around to doing data analysis. You should think, how much do they overlap in kind of a conceptual way? How much are they likely to be correlated in a more quantitative way? And you should really ask yourself, are they really measuring distinct things, or are they maybe measuring the same thing, or too much of the same thing? And to be clear, some amount of overlap, some amount of correlation is okay, but a lot of it is not okay. A lot of it is not okay either because it will literally produce problems with SPSS computing the regression coefficients for the model. You may, in extreme cases, get an error in your output saying, I can't solve this problem, essentially. Or even if you do get a model, you can really struggle to understand how to interpret those predictor variables given their high degree of overlap. So you should be thinking about these variables, maybe doing once you've gathered some data on them, doing some simple correlations on them. And once you start to run your analysis, you should definitely look at collinearity diagnostics like tolerance and VIF. Well, what do you do if you have a problem? Well, I kind of mentioned this in the last lecture. I think you could drop one of the predictor variables kind of on the rationale that they're really measuring mostly the same thing. You might say, look, we use different words or different terms for self-esteem and positive self-image, but on a practical level, they're really measuring mostly the same thing. Therefore, we're just going to drop one of them, drop the one that is slightly less correlated, I suppose, with the outcome variable. Or, and you sometimes see this in analyses, you can combine them. You could create an average of them. You could create a sum by a total of them by summing the two values, or some other composite factor where you're essentially decreasing the number of predictor variables so as to hopefully get rid of multicollinearity problems, or at least mitigate them a little bit. So those are just some suggestions. I'll try and return to these later on, if not in this lecture, I think in future lectures, because it's important to keep on thinking about this issue. But with that said, let's move on a little bit and talk about the main focus of today's lecture, and that is interactive models. And to introduce interactive models, I'm just going to propose a simple, or I'm just going to show a simple example, and that is, imagine you're a school psychologist who's studying academic performance, and you're doing a non-experimental design where you have predictor variables, amount of reading that students do in a particular class, and another predictor variable, the amount of class attendance they have, and an outcome variable, which is exam performance. And this is data which I'm pretty sure I originally got from Andy Field's textbook, Discovering Statistics Using SPSS. If you have access to my class, you can see the data set on Blackboard. If not, I'm almost certain you can find it on the website for Andy Field's book, and you can download it for free, I think, without even having to have purchased the book. If we wanted to represent this design pictographically, we could put our predictor variables and our outcome variables in a picture as so, and we could kind of ask the question, what's the effect of each predictor variable while holding the other predictor variable constant? We could think about this in terms of non-experimental or statistical control. What's the effect of attendance on exam performance if we hold constant the effect of reading? What's the effect of reading on exam performance if we hold constant the effect of attendance? That's what multiple regression allows us to do. So if I was going to do this analysis in SPSS, I would run it as a simultaneous multiple regression. I'm not trying to do any sort of hierarchical ordering, at least not in this example at this point. So I'm going to analyze regression linear. My outcome variable is exam performance. My predictor variables are text reading and class attendance, which you can see entered here in one block. And I'm just running a basic multiple regression. The output I get will look a little bit like this. I'll see that the model is significant, the model being the augmented model, and significant meaning in comparison to a compact model, it's statistically significant. The value for the F statistic's pretty big, the value for the P statistic or P value is really small, and maybe more importantly, we can see that the model, the augmented model that includes those two predictor variables, explains about 33% of the variance in the sample, or maybe if we want to think about the estimated effect size in the population, it's closer to 29 or 30%. So roughly a third of the variance in exam performance can be explained or is associated with the combination of class attendance and text reading. So if we wanted to interpret these results, we might say something like, a model that includes both of these predictor variables, that is the augmented model, is a better description or provides better prediction for the data than does a compact model that includes neither of them. Now, if we wanted to know about the incremental improvement of adding one predictor and then another, like does class attendance predict exam performance above and beyond text reading, or does text reading predict exam performance above and beyond class attendance, we could do this same analysis except adjust it slightly to be a hierarchical regression. If that's our research question, or if we have particular hypotheses that go in that direction, we can test them in a slightly different way. We keep with the analysis we're currently doing, that is the simultaneous multiple regression. We could take a look at our coefficients, and by looking at the values of the unstandardized and standardized coefficients, that is the slopes for those two predictor variables, and then looking at the little t-test, which tests whether those slopes are significantly different from 0, we see that both of our regression coefficients for text reading and for class attendance are significant, and how we could interpret those results is to say, look, text reading is associated with a significant increase in exam performance, the coefficient is positive, while class attendance is held constant, that is, controlling for class attendance. And we can say the other way, which is class attendance is associated with a significant increase in exam performance. Again, regression coefficients are both positive, while holding text reading constant. That's the idea of statistical control, and the way we might express that by interpreting regression coefficients. This type of analysis is sometimes described as an analysis of simple slopes, because essentially what we're saying is the effect, or the slope, of each predictor variable is significant and is constant across all levels of the other predictor variables. So the slope that describes the relationship between text reading and exam performance remains constant at different levels of class attendance, from very low attending people to very high attending people. The simple effect of one predictor is like the average effect across all levels of the other predictor variable. Now, if you're having trouble picturing what that might look like, take a look at this. It's a graph that I made in R Commander, which is a graphical user interface, or GUI, for the statistical program R. And unlike SPSS, it allows you to do some pretty slick looking, I think, 3D graphing. So here we have a 3D graph. Our y-axis is performance, that's our outcome variable. You can kind of see our two predictor variables, class attendance and reading. Our data is this cloud of dots in represented 3D space, and our model is this flat plane that is kind of slicing through the cloud of dots. And the point I was trying to make before is that the slope that, say, describes the relationship between reading and performance, we're constraining to be constant across all levels of the other predictor variable, attendance, and we can describe what that slope is. In this case, the slope for reading was basically 4.0. So for every additional unit of reading, we expect a 4-point unit increase in exam performance, and that slope, that increase, is the same whether someone attends class very little or whether someone attends class quite a lot. Now you may be thinking about this, what if that slope doesn't remain constant? What if it matters? What if the effect of reading counts a lot more if you're also attending class a lot, and counts a lot less if you're skipping a bunch of classes, or maybe vice versa? What if the effect of one predictor variable varied or changed across levels of the other predictor variable. If this happens, then we have a moderated effect or an interaction. Terms that you've probably heard before if you've done any amount of statistics in psychology, or even just read research methods textbooks or read journal articles. Interactions seem to happen a lot in psychology, and we're often rather interested in them. So how do we examine a moderated effect, or how do we examine an interaction in SPSS? It's really not very hard. The first step we need to do is actually make an interaction term. We have to make a term, a new variable, that represents the interaction between our two predictor variables, reading and class attendance. So what we're going to do here is use the transform compute variables menu here, or workspace. So go to transform compute variables. We have a new variable which I'm just calling re_x_att. That's a little bit of an awkward name, but what I'm trying to express there is the interaction of reading and attendance. You could name that anything you like, really, within the confines of whatever naming conventions SPSS has. You can even click on type and label and give it a fuller label to explain more fully what that means, like write an interaction term or something like that. The important thing is, whatever you name the variable, you have it equal to then reading times attendance, and you can either type those words into the numeric expression workspace, or you can drag and drop the variables in and use the little asterisk to represent multiplication, because we're literally multiplying reading times attendance, and whatever that product is for each person is the value that they have on our new variable reading times attendance. And so in the in the data set, once you've run this little compute variable command, you get output that looks a little bit like this, and you can see that this new variable has values which correspond to the product of reading and attendance. Now that we have our interaction term, we can include it in our model and see what effect, if any, it has on predicting our outcome variable. And how we often do this is we run a hierarchical multiple regression, where in our first step we include our main predictor variables, attendance and reading, and in our second step those predictor variables stay in the model, but we add the interaction term. So if you go ahead and do this in SPSS, at this point I trust you know how to, you'll get some output, and the output will look a little bit like this. Up near the top of your output, you'll have a model summary, and that will show you the effect size of our two augmented models, the first one containing only the main effects of our predictor variables, the second containing the main effects and the interaction term. What I didn't include here, I'm not sure why, is I didn't include change in r². If you ask SPSS to give you that, you'll get the difference between r² for the two models and a test of whether that difference is significantly different from 0. Now in this case we probably don't need it, because you can see that the first model, containing only reading and class attendance and reading, explains about 30% of the variance in the population, and the second model that includes the interaction explains 35%, and I'm guessing that's going to be big enough to be a significant improvement. And we might say something like including the interaction term significantly improves the fit of the model to the data. We can also see the ANOVA table down at the bottom. That's just testing each augmented model by comparing it to the compact model that has no predictor variables in it. So is the first augmented model, including only class attendance and text reading, significant compared to the compact model? Yes, it is. And is the second compact model, or I'm sorry, second augmented model, which includes class attendance, reading, and interaction, significantly a better fit for the data than the compact model? Yes, it is as well. Kind of unsurprising, to be honest. Now, if we go down and look at the coefficients for our regression models, things get kind of interesting, because you can notice here that when the interaction term is included in the model, it is statistically significant. So if you look at the value for the t-statistic and the p-value for the interaction term, it's a significant effect. And you can also notice that the main predictor variables, text reading and class attendance, which are significant on their own, are no longer significant when the interaction term is in the model. This sometimes happens. This we often kind of like to see this happen because it suggests a relatively strong interaction, such that the interaction explains most of the effect, and the main effect of the two predictor variables kind of disappears when the interaction term is present. That doesn't always happen, and indeed in later lectures I'll talk about some of the nuance in interpreting models in which the interaction is significant. But for the time being, let's just try and make a relatively basic interpretation. And that would be something like this. When the interaction is in the model, text reading is associated with a significant increase in exam performance, while class attendance is held constant at 0. Also, we could say class attendance is associated with a significant increase in exam performance, while text reading is held constant at 0. Now, the key thing to notice here is that when we're talking about a model that did not include an interaction, as I did earlier on, our interpretation of the main effects of each predictor variable is that they exist across all levels, or across an average of the other predictor variable. When an interaction term is present, that interpretation changes a little bit, and we're saying, look, the effect of this particular predictor variable changes, but here's what it's like when the other predictor variable is at 0. As you might guess, if you think back to our discussion of centering predictor variables, we can adjust this through centering, so we can say, while the other predictor variable is held constant at its mean, for instance, which is sometimes more interesting or more important. Here, because it's possible that someone could read no amount of text or could attend no amount of classes, I have a feeling that happens sometimes in classes I teach, it's probably meaningful to talk about predictor variables which have 0 values. And so we could say, look, text reading has this particular effect when class attendance is at 0. Class attendance has this particular effect when reading is held constant at 0. Maybe a general important point to make here is that when an interaction term is in the model, the main effects themselves become more difficult to interpret. They're conditional, or sort of provisional on each other. It can sometimes even be really impossible to talk very much about main effects if an interaction is present in the model and if it's strong, because those main effects depend somewhat on each other. So when the interaction is in the model, the effect of text reading changes across levels of attendance. And to put it the other way, the effect of attendance on our outcome variable, performance that is, changes across different levels of text reading. If you're having a hard time visualizing this, let's go back to that image I made in R Commander. And I couldn't do this in R Commander, at least not in the version I was playing with at the time I did this slide. But imagine now that instead of having a flat plane that slices through this cloud of dots, the plane is warping, it's changing. And I'm trying to illustrate this here with some lines, like that, this. Imagine that blue plane is kind of warping such that the slope that describes the relationship between, in this case, reading and performance, gets steeper at different levels of attendance. So it's no longer really meaningful to say, well, what's the effect of reading on performance? The truthful answer is, well, it kind of depends. It depends on what level of attendance the person is at. That's the essence of an interaction. By the way, if you're enrolled in my class, or if you just have a copy of Andy Field's textbook, which I highly recommend you buy, you can see a nice illustration that he makes based on some research on aggression and video game use, which is a sort of a popular, if somewhat controversial, area of research. And so here on the left side of the image, you see a model in which video games and callous and unemotional traits, that's a personality trait, are not interacting in their prediction of aggression. That flat plane there suggests that they're not interacting. And then on the right you see a model in which there is an interaction term. And if it's not obvious at this point, I should make it clear that SPSS, when you're using the regression module, doesn't make those interaction terms for you. You as the researcher have to decide, do I think that these variables interact, or am I curious about the possibility that they could interact? And if the answer is yes, and it often is, then it's on you to make that interaction term, it's not very hard, and include it in your model. SPSS won't do that for you. Later on, when we get to Unit 3 of this class, and we're talking about ANOVA type designs and analyses, the ANOVA module, the GLM module in SPSS, just kind of for reasons of tradition, automatically make those interaction terms for you. In the regression module, it doesn't. But the good news is it's not hard to make those terms yourself and to test them and interpret them. And if I've been a little vague about interpretation, don't worry, because in the next lecture and the following lecture, I'm going to really drill down on different ways that you can interpret regression coefficients in models that include interactions, which are the type of models we often study in psychology. And with that in mind, let's do a practice example. Imagine you're a clinical psychologist who's studying eating disorders using a non-experimental design. Again, if you have access to Blackboard and you're enrolled in my class, you have access to this eating disorder data set, and I encourage you to download it and play along with it, play along with me as I go through these analyses. So let's imagine in this example that we have some predictor variables like self-esteem, negative body image, a thin ideal that's endorsing the belief that being very thin is an ideal way for you to be, and exposure to media, perhaps particularly media which exemplifies images of beauty that are perhaps unattainable for most normal people. And our outcome variable is eating disorder symptoms. So we imagine that all of these predictor variables are probably predicting our outcome variable, eating disorder symptom. But let's imagine that our primary hypotheses are going to be based on self-esteem and negative body image, because these are most related to existing theories that try to describe why people have eating disorders. And so when we designed this study, we're principally interested in those two predictor variables. However, because we had the opportunity to gather data, we included some other questionnaires, and so we have these other variables, but for us, they're kind of secondary value. So we're maybe thinking of them as kind of exploratory analyses, or we have exploratory hypotheses about them that we're interested in, but just not as much. Now, again, I'm just kind of making this up as I go. You, depending on the type of research you're doing, may have some analyses which are of primary importance and some which are of secondary importance. This is just an example that I kind of came up with. As usual, if we want to represent these pictographically, we could draw an image that looks a little bit like this. Here are our predictor variables. Here is our outcome variable. That's pretty simple. And because we have this kind of primary and secondary ordering in the way we're thinking about these variables, it seems most appropriate to do a hierarchical multiple regression. And in step 1, let's go ahead and enter self-esteem and negative body image. They're kind of our main predictor variables that we're particularly interested in. And then in step 2, those variables stay in the model and we add thin ideal and media exposure. So if you're working on SPSS, just go ahead and run the usual analyses with your hierarchical regression. So get the usual statistics, diagnostics, graphs, etc. At this point, hopefully you're kind of familiar with this whole process. And my goal today is just to walk through the output so we can take a look at what we find and maybe address some important concerns. So here's some output from our hierarchical multiple regression. We have two models, really three because there's the compact model, but we have two augmented models, and both models are significant. But the addition of those exploratory variables doesn't significantly improve the fit of the model. And the reason I know that is if I look up at the model summary, I can see that the first augmented model, including just negative body image and self-esteem, explains about 61%, 62% of variance in the outcome variable. And that's, of course, significantly different than nothing, which is what the compact model is explaining. Then if we go and add in our second augmented model, we add in thin ideal and media exposure, we go up to about 61 to 64%. There's a slight increase of about 1% of variance explained, and unsurprisingly that R squared change of 0.01, 1%, is not a big enough improvement to be statistically significant. So we might conclude that, gosh, these additional variables, they were of secondary importance anyway. They don't really do a lot to improve the fit of our model. Now if we move on and take a look at some of the coefficients for our two augmented models, we can see that the values for the regression coefficients for thin ideal and media exposure, our two kind of secondary importance variables, are relatively small. The standardized coefficients for those two variables are smaller than the standardized coefficients for the other two variables, and also the t-tests, testing whether those unstandardized values are significantly different from 0, those t-tests are not significant. So we might conclude thin ideal and media exposure don't seem to significantly predict the outcome variable eating disorder symptoms, at least not when we have a model that controls for negative body image and self-esteem. Because we did a hierarchical multiple regression, SPSS kind of wants us to reports to us the variables which are not included in each step of the model. So at step 1, augmented model version 1, we're not including, I should say, thin ideal and media exposure. And SPSS kind of warns us like, hey, these variables, at least thin ideal, have fairly low tolerance, not desperately low, but fairly low tolerance with the other variables which are already in the model. Kind of a warning that adding them into the model may not really work all that well. There may be some problems with multicollinearity. Based on the presentation earlier in this lecture, you might be wondering, do we have a problem here with multicollinearity? Well, if you ask for it, SPSS will give you some correlations and also some collinearity statistics and collinearity diagnostics. For the time being, I'm not going to address the table at the bottom here, but if you just look at the table at the top, you can see that the tolerance values for negative body image and for self-esteem, for negative body image and thin ideal are relatively low. Not desperately low, but relatively low. Now, what's going on here? If we wanted to look at this a little bit more closely, we could look at the correlations which are presented in SPSS's regression output, but we might want to pop over to the correlation workspace and just do some basic bivariate correlations. So analyze, correlate, bivariate, and look at the correlations between all these different variables. If we do that, we can see that thin ideal is highly correlated with negative body image. This suggests a condition of redundancy or collinearity between these two variables. And this creates statistical and interpretive problems. Media exposure is uncorrelated with the outcome variable, so that's also kind of an issue that's problematic and means it can't do too much in the analysis. So what should we do about all of this? Should we drop our exploratory variables? Probably we should. Including them doesn't really help the model in terms of improving the fit. We don't get a big change in R-squared, and including them also hurts the model in the sense that it introduces multicollinearity. But if we do drop these variables, we should be pretty honest about the fact that we at some point included them. So if you're writing up your results or if you were describing them to a colleague, it's important to say initially we included these two variables for some supplemental or exploratory analyses that didn't really pan out. Because let's be honest, if you had found a kind of a significant and apparently robust effect for either of these variables, you probably would have reported it in your results section or on your poster or in discussions with a colleague. It's probably fair or most fair or most honest to say, yes, we included these variables initially, but due to their relatively poor predictive power and due to concerns about multicollinearity, we dropped them and then reran the analyses, or we dropped them and used only our initial primary variables of interest. Hopefully that all kind of makes sense to you, but just to round out this presentation, let's get some more practice looking for things like outliers and thinking about assumptions, kind of like we should always be doing. If you asked for them, which you probably should have, you could ask for some case-wise diagnostics, looking for cases that have extreme values in terms of their residuals, or you could just save out values of residuals and standardized residuals and then just sort through the data set to see them yourself. And here you can see there are two cases that have fairly large standardized residuals. Now, two cases out of 30 or 40 or however many data cases I have in this data set isn't that big a deal. We're allowed to have a few of these high values for our standardized residuals. But if we had a lot of them, or if we had some that were really, really high, like 3s and 4s, we'd definitely be kind of worried. In this case, probably not too much of a problem. Moreover, if we sort our data sets and identify these two cases, here I'm sorting by some of the influence statistics that I've computed, you can see that these somewhat outlying cases with respect to their residuals don't seem to exert a lot of influence on the model. So if we look at some of our measures of influence like Cook's distance and leverage and some of our DF betas and so on, these particular cases don't seem to do an awful lot to influence the model. So they're probably not real outliers, or at least very problematic outliers, and moreover, they're not exerting, as far as we can tell, a ton of influence on the model. So further evidence that we don't need to worry about them too awful much. We should probably look at the distribution of residuals, like always. So there, as you know at this point, a lot of different ways you can create histograms or probability plots, PP plots for residuals. Here I forget exactly how I did this. I think I used the explore function, but you could also use some built-in stuff in the regression module, and you can see that the distribution of residuals looks more or less normal. It certainly doesn't look particularly skewed. There's some non-normality to it. But that non-normality is not statistically significant. So if you look at the tests for normality for the standardized residuals, or for that matter for the unstandardized residuals, those tests, the Kolmogorov-Smirnov test and Shapiro-Wilks test, are not significant, suggesting that these distributions do not differ significantly from a normal distribution. Remembering, of course, though, that these tests, KS and SW, tend to be a little bit underpowered, so they're not that great at finding deviations from normality anyway. But in combination with the graphs, we sort of think like, yeah, these residuals are pretty normally distributed, which is good because, again, we assume that our residuals should be normally distributed. If you looked carefully, you probably saw that back when I was running through the regression module, I asked for a plot of standardized residuals against standardized predicted values. The reason I did this is I wanted to look at the variability in the variance of these residuals at different levels of the predicted value. Now, in the case of a simple regression, we might just plot standardized residuals against the predictor variable because there's just one predictor variable. In the case of a multiple regression where we've got two or more predictor variables, it's a little bit easier to plot it against the standardized predicted value. What we're looking for here is evidence for whether or not the variability in the residuals is wider or narrower at different levels of prediction. Is it the case that, say, at low levels of our predicted variable, or low levels of prediction, we get relatively narrow, a narrow range of residuals, and at high levels of prediction we get a really broad range, or vice versa? That would be problematic because it would suggest that our model is biased at some levels of prediction. It makes bigger errors at some levels of prediction than it does at others. Here we see a relatively uniform pattern of residuals. You know, the values are not particularly more spread out at one level of prediction than they are at another. And remember, this is important because homoscedasticity, the assumption means equal variance of residuals at each level of our predictor variables. So and this is kind of a bit of a blurry graph, but the idea here is if we are trying to express the residuals, the little errors, at each level of our predictor variable, those errors, those residuals, shouldn't spread out much more at one level than they do at another level. And here in this image, as kind of crummy as it is, they more or less don't. Heteroscedasticity, that's kind of the opposite condition, suggests that the model is worse at some levels of our predictor variable or predictor variables than at others. So here you can see an example of homoscedasticity. Those errors are kind of uniform in how spread out they are at each level of whatever the predictor variable is. You can also see an example of heteroscedasticity. At higher levels of the predictor variable, the residuals spread out a lot more, and that should concern us. This is an image from Andy Field's textbook, and you can see some different patterns that sometimes occur. What you want to see is a pattern that looks a little bit like the top left box, where there's kind of a cloud that's sort of roughly square or rectangular in shape, suggesting at different levels of the predicted value of the outcome variable, the amount or the sort of the range of residuals is about the same. What you don't want to see is almost anything else, like these weird sort of funnel or sinusoidal patterns, suggesting that the patterns of residuals shift around a lot at different levels of prediction. That can suggest a violation of this assumption, the assumption of homoscedasticity of residuals, and relatedly, problems with bias. Alright, so far we haven't had any real problems with outliers, we haven't had any real problems with violated assumptions, just to make that point clear. To kind of further on our discussion and to kind of wrap things up, let's ask, can we improve the model at all? Can we make it predict or describe the data any better? Well, maybe we can, and we've been talking a lot about interactions, or at least I've been talking a lot about interactions. Could we include an interaction term in this model? Sure we could. We could do a hierarchical multiple regression in which our first step includes our predictor variables that we're principally interested in, self-esteem and negative body image. And then in step 2, we include the interaction of those two terms. And again, to be clear, hopefully we have some good reason for including this interaction term. Maybe there's research that suggests that these variables interact, or there's clinical experience that leads us to think that they do, or there are theories which say that the interaction of these two variables, these two constructs, are important. So let's test that. Let's include an interaction term. To represent this pictographically, we're basically just adding a predictor variable, that being a predictor variable which represents the interaction of our two main predictor variables, kind of like this. Now, making the interaction term is pretty easy. I'm not going to show how to do it again. Here I've just run my hierarchical linear regression, or hierarchical multiple linear regression, and you can see that the change in R squared is significant. So with just our two main predictor variables, we're explaining about 63% of the variance, but when we include our interaction term, it goes up to maybe 64 or 65% of the variance. Now that's not a huge jump, it's a jump of maybe 2 or 3% of the variance, but it's enough to be statistically significant. So we might conclude that, or we might interpret these results to suggest including that interaction term improves the fit of the model to the data. Now if we slide down and look at the coefficients for our models, we can see that the coefficient, the regression coefficient for the interaction term, is statistically significant, and its size in terms of its standardized coefficient is fairly large, kind of relative to the other predictor variables in the model. And we also can see here that the interaction term, of course, is excluded from the first version of the augmented model, that's model 1, but we'll see here that we can add it in to the second version of the augmented model, model 2, as we of course did. Now this excluded variables table is actually sort of interesting, because what it's giving us, in a sense, is a preview for how a particular variable, in this case the interaction term, will behave once it's added to the model. In model 1, the interaction term is excluded, so you can see it's on the list of excluded variables, but we get a preview in a sense of what its beta, what standardized regression coefficient will be if it is added into the model, which of course it is at step 2, or model 2. So we get the value of the beta, and we get the significance test, and we can kind of conclude like, hey, it will be statistically significant if we add it to the model. Well, what about multicollinearity? You might notice here that the variance inflation factor is pretty high and the tolerance is pretty low, and that's bad. But we actually would expect this, since the interaction term is literally made from those two predictor variables, so it's going to be correlated with them. The fact that there's a high correlation between an interaction term and the predictor variables that make it isn't necessarily a problem. It's something we often expect, and indeed there's a way to reduce that multicollinearity, which I'll talk about in a future lecture. Moving on, if we look at some more collinearity diagnostics, the tolerance values are all fairly low, but again the interaction is in the model, and this is kind of to be expected, so we're not necessarily all that worried about this. And the bottom line is we might conclude, based on all these results, that including an interaction of these two main predictive variables gives us a better way of describing or predicting the data. Now, what I just said is pretty vague. You might be asking, well, could you give me some more details about that? And I say, well, yeah, I can. In the next lecture, I'm going to give another example to practice looking at interactions, looking at moderated effects, and we're really going to drill down on how to interpret regression coefficients in situations where interactions are significant, because it takes a little bit of work. This type of analyses, again, is sometimes called simple slope analyses, and it's, I won't say it's tricky, but again, it takes a bit of work when interactions are present in the model. So I didn't really have time to get into it now. We're closing in on an hour, which Lord knows that's a lot of talking, a lot of listening. Let's take a break. Make yourself a cup of fine tea or coffee or whatever your preference is, and relax and think about this stuff, and hopefully it'll make sense to you. Hopefully you'll have learned something. If not, let me know. Hit me up in the comments section on YouTube. If you're in my class, ask me a question in class or email me a question. I'll do my best to answer all of them. Thank you so much for your attention. I always like recording these videos, even though sometimes it seems a bit hard and I stumble and I have to re-record stuff. I do genuinely enjoy talking about this stuff, and I hope you enjoy listening, or at least you learn a little bit from listening to me. All right, bye-bye.